Oscillations and Waves. Simple harmonic motion. In order for an oscillation to be considered simple harmonic motion, two requirements must first be met. The first, when the body is displaced from equilibrium, there must be a force that is trying to bring it back to equilibrium. That force is called the restoring force. The restoring force must be proportional to the displacement of the body. The two most common examples of simple harmonic motion are mass on a spring and a pendulum. When displaced from equilibrium on both the spring and the string, a force continually tries to bring the body back to its original state. Waves. A wave is the propagation of energy through matter. There are three types of waves. The two main types of waves are longitudinal waves and transverse waves. The key difference between the two is the particle motion, or how the particles move. In longitudinal waves, the particle motion is parallel to the direction of the energy transfer. If the energy is traveling to the right, then the particles are going that way too. In transverse waves, the particle motion is perpendicular to the direction of the energy transfer. In everyday life, waves are more often depicted as transverse waves. If the energy is traveling to the right in this case, the particles are going to travel up and down, perpendicular to the energy transfer. An example of a longitudinal wave is sound. Music coming out of a speaker will travel through compression and rarefaction until it reaches your ear. In longitudinal waves, the parts of the wave where the particles are close together are the compressions, and where the particles are farthest apart are called rarefactions. In transverse waves, the point where there is the most positive displacement from the mean is called the crest. The point where there is the most negative displacement from the mean is called the trough. An example of a transverse wave is a water wave, where the water goes down and comes back up repeatedly. Before we look at the third type of wave, let's examine the details of a wave first. Let's start with displacement. Displacement is the distance of the oscillating object from equilibrium. Now, the maximum displacement, or the distance from equilibrium, is known as the amplitude. The amplitude is what determines the intensity. Taking the example of sound, the amplitude would determine the volume of the sound. A high amplitude would sound like this, and a low amplitude would sound like this. Next up is the period. Period is the time it takes for one complete cycle. The period of this wave is 2.66 seconds. The period is directly related to our next term, frequency. Frequency, by definition, is the number of complete cycles of an oscillating particle per unit time. Let's say that 1 unit of time is 5 seconds long. The number of complete cycles within that unit of time is the frequency. In equation form, frequency is equal to 1 over the period, and the period is equal to 1 over the frequency. The SI unit of frequency is a hertz, which is equal to 1 cycle per second. So generally, frequency is a measure of the number of cycles per second. 2 hertz means there are 2 cycles per second. Taking the example of sound again, the frequency determines the pitch of the sound. A higher frequency would sound like this, and a lower frequency would sound like this. Our next term is wavelength. The wavelength of a wave is essentially the length of the wave. It's the distance between two successive points on a wave. It can be the distance between one trough to the next trough, or one crest to the next crest. It just has to be the distance between two successive in-phase points. Our final term is wave speed. It's the speed at which a given point on the wave is traveling through the medium, or in other words, how far a particular crest travels per second. There's an important equation that ties together these last three terms, the frequency, wavelength, and the speed of the wave. It states that the wavelength is equal to speed over the frequency. This can be rearranged, of course, and we can use this equation to find the frequency and the speed as well, given that we are provided with the other two. We can see that the equation follows the definitions of frequency and wavelength. Since the units for frequency is cycles per second, and the wavelength is meters per cycle, when we multiply them together, we get meters per second. Frequency times wavelength is equal to the speed. Now for the third type of wave. The last type of wave is called a standing wave. This type of wave is formed when two waves approach each other with the same speed, same amplitude, and the same frequency. This wave is usually a reflection of itself traveling in the opposite direction. There are two important parts of the standing wave: nodes and antinodes. The nodes on this wave are the points where the wave is completely stationary. The antinodes are the points of the maximum displacement in a standing wave system. An everyday example where we find standing waves is in a microwave. That's why there's a turntable, so that all the food gets heated, there won't be cold spots where the nodes are. Electromagnetic waves. Electromagnetic waves are transverse waves that travel at the speed of light, which is 3 × 10⁸ meters per second, in a vacuum. The different types of EM waves are determined by their wavelengths. The electromagnetic spectrum is divided into these 7 sections: gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwaves, and radio waves. Listed from lowest wavelength to highest wavelength, or in other words, highest frequency to lowest frequency. The speed in this case is the constant c, or the speed of light. This is the little bit of the EM spectrum that we can actually see, and that is divided into the different visible colors. Different colors are consequences of different wavelengths as well. Violet has the smallest wavelength and red has the greatest. And that is the intro to waves.